you adorable boy. He's my loyal student. Okay. Thanks for watching, my loyal student. Watching. Hi everyone. Welcome back to my math teaching online today. Today in this video, I would like to show you our continuous lesson of finding the area under the curve. However, we will step one more further step, which is finding the area between the curves. So in the past, you have learned how to find the area under the curve by two techniques. One is three-dimensional sum, divide them into small strip rectangle and taking the limit and adding the total area of these small strips together. That is the three-dimensional sum. And then another technique, we just use the iteration and very easy to do that. So the lesson today is easy to do as well. We just use the iteration method, finding the area between the two curves. So let's take a look at my lab diagram on the board. On the board, I have two functions. The first function is a quadratic function and has the equation of y equals x squared plus 1. The second function is the straight linear function, go to the origin 0, and the equation of this function is y equals x. Now, in order to name it and for convenience, I'm going to call the first function is f of x, and the second function is g of x. So I have f of x is a quadratic function, and g of x is the linear function. To find the area, which is the shaded area here, in the between these two functions, and we are going to iterate them from 1 to 3. So the region, shaded region in between this curve here is the area we want to find. Ignore the blank area underneath here. We don't need to find this area, right? Our purpose is to find the area between these two curves. Now, in order to find the area between these two curves, you need to find the differences between the above curve and the function below. So we have the quadratic function. So make observation. We have the quadratic function above the linear function. Obviously, you can see it, right? So in order to find the area of this, basically, we're going to use function f of x because it is above, subtract the function g of x because it is below, right? And in order to find the area of this, we have to find the rate of change of the area underneath the curve. And the rate of change of this is a pi of x. And a pi of x will be equal to f pi of x minus g pi of x. So remember from the concept of the first previous lesson, we acknowledge that the function here, the original function here actually is the derivative of the area under the curve. So if we if we substitute the function, right? Remember, this is the derivative. This is the function f prime of x. So x squared minus, no, plus 1 minus g prime of x is x. This is the result of these two functions subtract each other. And they are the derivative of the area under the curve. So the function itself is just the derivative function of the area under the curve. To find the area, we have to take the integration. So I'm going to take the integration of this, and our integration from 1 to 3, 1 to 3, and I'm going to substitute this in. So x squared plus 1 minus x dx. So now we have to find the area function. And the area function of the result of these two functions subtract to each other equal 1 over 3 x to the power 3, right? We do the antiderivative. Plus 1 here become x, and minus 1 over 2 x squared. So this is the area function, and we're going to integrate it from 1 to 3. So I'm going to continue with this result. So our A of x area will be equal 1 over 3. I'm going to substitute the 3 here for the value of x to power 3, adding with 3 for x, minus 1/2, and x is 3 square, minus 1 over 3, and x here is 1 to power 3, adding with 1, minus 1/2, and x here is 1 to power square, and close the bracket. So how much it will be? Now I have, this is 3 to the power 1, this is 3 to the power 3. I can cancel this with down here and make this 3 to the power 2. And 3 to the power 2 is just 9. Adding with 3, minus, this is 9, 3 to the power 2 is 9, minus 9 divided by 2, right? And then minus, this is 1 over 3. This is minus 1 over 2. So let's calculate this. This equals 9 add 3 is 12. Minus 9 over 2 is 4.5. Minus, this is 0.5. Adding with 0.3, so 0.8. Okay, so this is 0. Yeah, let's just make it 0.8. Just round off. So this is 0.8. And our answer will be what? 12.5. Okay, so 4.5 and 0.8 will be 5.3. So 12 minus 5.3 will be equal, 12 minus 5 is 7. So 6.7. Yeah, so that is the answer for this area. Okay, so that is not so bad. It's very easy. Just use the integration and just make sure you use the above function, subtract the below function. So after we use these two functions, subtract each other, we integrate we get back to the area function, and this is the area function. We evaluate from 3, between 3 and 1, from 1 to 3. And this is the result we got. So the area for this piece here equals 6.7. So the answer for this is 6.7 unit square, whatever, right? Unit square. Okay, so that's how we do the first question. Now I'm going to progress to show you the next question. And to do the next question, it's a little bit more complicated. So what is the difference between the first question and the second question here on the board? I'm going to show you. I don't know why it takes me, I have to spread very hard to erase this board, otherwise it is not working very well. So maybe because the chemical I use on it when I erase the board to clean it. Okay, I have to reconsider the stuff. And sorry for taking my time to do this. Okay, so the second diagram, you have a two curve. One is the y equal cos of x, and one is the y equal sine of x. If you know how to sketch the cos x and sine x function based on the trigonometric lesson you have learned in the past, then you see this shape is just the way it is, right? So we have the shape of the cos of x. Now we haven't finished the home function. The home function should be like the wave look like this, right? But we just mark the from here to here for the cos function, right? So we ignore the down here function by a dotted line like that, okay? But that's the cos function. Cos function start from the 1 unit on the top, and the sine function is start from 0. So it's very easy to distinguish between the two functions. It's not a big deal, right? Cos always start from the maximum always at 1, and the sine always start at the origin 0. And yeah, so that is the sine. So this curve here is a sine, and this curve here is a cos, as I mark it on the board. Also, we want to find the region R1 here, the shaded region here I call R1, and the shaded region here I call R2. So what we're going to do in this question, we're going to find the area of R1 and the area of R2. Now you notice that this question is different from here. As I show you, each question is slightly different. I don't want to show you the same question all the time, right? That's how I approach to my course teaching. I approach each question variety, but it's slightly different. So lead you step by step to be able to perform one step at a time. And we go up to the next step, further a little bit. That's the way I design my course. So you will learn my course in a very easy way because I don't jump. I don't jump from one, suddenly jump to another level, right? I connect this level in step by step and logically in a sequence as the natural of the math language. So of course, I need to advertise for my course online, so I get more students and get more clients like you to buy my online course. And in order for you to understand what's benefit you buy my course, I have to explain it to you so that you know that I progress the course, I design the course in a progressive structure and step by step in a sequence and logically so that you can learn more easily. If you at the right level, you learn my course, you feel it very easy. If you're not at the right level, you jump in from grade 9, you took on calculus, of course you will have problems, right? So I hope that this course is designed for Math 12 students, and only Math 12 students interested or need to purchase this course to learn for their math in university. Because again, I told you, if you have to take math course in university, unless you are very strong in the subject already, I'm not saying about that, then that's a different case. But if you're not very strong and you forget a lot in math, then you need to take my course before you get into university. So anyway, I will get back to solve this question right now. So this question, you will find the region R1 and region R2. Notice that this is the middle intersection between the two curves. So you have a two curves here intersect at one point. And we want to find the region where these two curves, between these two curves, right? The region between these two curves. And depend on the shape. In this case, we have two regions between the two curves. In this case, you only have one region to find, right? But in this case, when we draw the curve, turn out we have two regions. So therefore, we will find two regions, okay? So let's do one by one. When we're going to take a look at region 1 here. So the region 1, we have to notice what curve is above and what curve is below. The above function is the cos x. The below function is the sine x, right? This is the sine x continue here, from here all the way to here. So this is sine x and this cos x, and the cos x be above the sine x. So we're going to say R1 will be equal to cos of x minus sine of x. And we're going to do integration of R1. We're going to integration of this actually arc right? The area between the curve is actually a derivative of the area. And the derivative here is cos x minus sine x. So what we're going to do, we're going to integrate this derivative to make antiderivative to get back to the region function. So cos x minus sine x dx. And we're going to integrate. Let's take a look at the integration region from 0 to pi over 4, right? This is at pi over 4. So we're going to say from 0 to pi over 4. We're going to integrate this. And integrate this. Antiderivative cos x is sine x. Minus antiderivative sine x is minus cos x. So minus with minus, we have two of them, right? It turned out to be positive. And we're going to integrate from 0 to pi over 4. So the sine of x is, we're going to substitute by this angle, x is pi over 4. Adding with cos of x is cos of pi over 4, minus everything here is 0, so sine of 0, and minus cos of 0, right? So now sine of pi over 4, everybody know that, equal 1 over square root 2. Adding with cos pi over 4 also equal 1 over square root 2. And minus sine of 0 Sine of 0 here is 1 and 0. So sine of 0 is just equal 0. But cos of 0 will be minus 1. So this is 1 at 1 is 2. 2 over square root 2 minus 1 is the answer. Now, if we don't like the square root underneath here, we can rationalize it, and that will become 2 square root 2 underneath 2 minus 1. So the 2 here will cancel with this, and will give us the answer of square root 2 minus 1. And that is the area of the first region. So that equals R1. So we find out that's our R1. Now I'm going to find the next. I'm going to have to find R2, right? So let's find out the region R2. And again, how do we find the region R2? We're going to make observation of which one is the area, is the function above, and which one is the function below. So I'm going to find R1 now, or R2 now. So our R2 region, actually R prime 2, right, will be equal. The first function above is sine x, so it's reversed, right? When we look at this region, the function sine x is above, and the function cos x is below. So we have to use the sine x minus the cos x now. So it will be sine of x minus the cos of x. And we're going to do this iteration from, now if we use this sine x as the above, it will be what? The region from pi over 2 to pi over 4. We go backward this way, right? Pi over 2 minus pi over 4. So here will be pi over 2, and down here will be pi over 4. And we need to put the derivative in here, sine of x minus cos of x dx. So now we're going to take antiderivative of this. Antiderivative of sine x is minus cos x, right? Antiderivative of sine x, so that will be minus cos x, and minus antiderivative of cos x is sine x. So we have minus cos x minus sine x. We're going to integrate from pi over 4 to pi over 2. So now I'm going to integrate it. I'm going to substitute the value in, right? So I have minus cos of x is pi over 2 minus sine of x is pi over 4 minus cos of x is, sorry, my mistake here. It should be sine over 2, right? Sine pi over 2, and then minus cos of pi over 4 minus cos of pi over, and actually minus with this minus because we have this negative, right? So we use this, subtract this, but we have 2 minus here, so that becomes positive. So adding with cos of pi over 4, again, for this as well, it's supposed to be minus, but minus with minus become positive. Sine of pi over 4. So the answer for this, cos of pi over 2, this is our pi over 2 here, right? And the coordinate for that is 0, 1. So cos is 0. So this equals 0. Okay. Sine pi over 2 is 1. So we have minus 1, right? Because that's minus sine pi over 2 is 1. Adding cos of pi over 4, of course is 1 over square root 2, right? 1 over square root 2, right? Cos. So 1 over square root 2 adding with 1 over square root 2. So now we're going to continue to calculate this. So it turned out we have the same value, right? And you can see that the reflection here show that these two regions actually is the same size, these two regions, right? It's just one on the left, one on the right, so they should be the same numerical value. So this will be the same like the other one, region 1, square root 2 minus 1. So now we're going to add them together, region 1 and region 2 add together, or we can use the same numerical value multiply with 2, right? So we add R1, add R2, our region will become 2 times square root 2 is 2 square root 2, minus 1 is minus 2. So our final answer for these two regions, so area will be equal 2 square root 2 minus 2. That is both R1 and R2 equal. Okay, so I have shown you how to find the area between the curve, and that's the ways you do it. So first you make the observation which one above which one. You use the above one, subtract the below one, and you iterate according to the region. If you take this region, you iterate from 0 to 4. If you take this region, you iterate from pi over 2 to pi over 4 because this curve above this curve. So this curve is pi over 2 ended up here from the coordinate here, minus with this curve is pi over 4 to iterate for this region. So now, as the end, you add two regions together. And that's the answer. So I hope it's very clear to you, right? This topic is not so bad. So I'm not going to summarize a lot. What I just want to show you, right, is one more thing I would like to mention before I end this video. Okay. Now, you will have other questions as well in this practice exercise. And the other question, of course, will be different from these two questions I show you, right? So let's say if you have a curve look like this. You have a quadratic like that. And then you also have another quadratic go this way. Let's say like this. And you want to integrate the region between them, this one here, the area here. So to do this, you have to find the two intersection point. One is here, which is 0, 0, the origin, turn out to be in this case. And you have to find the intersection here so that you know what number here. Is that a 3 or is that a 4 coordinate or is that a 5 or 6, right? You have to find out. So to find this, you just say if this is F1 and this is F2, then you set F1 equal F2 to find the intersect between the two curves and solve for x coordinate so that you know how much is the numerical value here if they haven't given it to you. But if they give it to you, then that's straight. You don't have to do this process, right? So after, sorry, I have another like a phone call and I don't think it's important. Sorry about that. So after you iterate the, you find the intersection between the two curves like this, then you just proceed the same like this way I show you. And for example, this is one of example I show you, right? What about if you have another curve look like this? And I just want to give you a hint so that you can do that. So let's say you have a curve look like this. This is we call a 1 over x function, rational function. You also have a curve look like this. And this is minus 1 over x, just the reduction over the x-axis, right? And you have to integrate from 1, let's say, to 5. And therefore, the region here will be the home piece here. So you will use 1 minus x, subtract 1 over x. That will become plus, right? 1 over x plus 1 over x. And if you know this is the derivative, so you have to do antiderivative this function and figure out like the rest I show you. So that's it. That's how you learn how to find the area between the two curves. So I guess the topic today is very easy to follow. I hope so. And I will upload the practice exercise for you in this unit, then the unit quiz as well. And I see probably we will progress to the next unit. For the next video, maybe you, maybe because this calculus course is it's more complicated than the first one, so maybe I do a summary on the question we have learned so far. I will pick up one from each unit and do a summary for you before I give you the quiz or the final exam from my course. So maybe I will show you on the videos about summarization of what we have learned so far after the next unit. So the next unit will be, stay tuned for the next unit we call a volumes, area and volumes of the solid revolution. And that topic, as well as the topic of the sigma notation I have shown you in the past, they are similar to the first year calculus course in the university. So some parts of my topic in the second course is not just Math 12, but they are adding some similar equivalent to the first year of university. Not all of them, but some parts of it. And I hope that you will have a good time if you finish my course and then you take the course in the university. That will tremendous gain for you, to be honest with you. Anyway, thanks for watching, and I will see you in the next video.